All right, so in this video we're going to talk about phase lines, which is sort of like a slope field. It is a slope field. It's a special slope field for a specific type of differential equation. So the first thing we need is the type of differential equation we're going to look at. So here's a definition for an autonomous. So an autonomous differential equation is dependent. I don't want to use that word because I'm going to use dependent in a different spot. An autonomous differential equation contains only the dependent variable. Dependent variable. So an example of an autonomous differential equation that we've seen before would be like dy dt is equal to some constant, and I'll call it alpha here, times y. So because it only has y on that right-hand side of the equation right there, and that is the dependent variable from that differential equation, that makes it an autonomous differential equation. Now, if I were to do something like plus t, then this part of it makes it not autonomous. Right, so we need to have basically only y's. We can have other numbers, but only functions of y's on the other side to do this. All right, now what we're going to do is we are going to, at least for phase lines, so how about here's some steps for creating phase lines. So the first step for creating a phase line is to find out where it has an equilibrium solutions. So let's find the equilibrium solutions. Now recall that equilibrium means no change, and no change means derivative equal to 0. So you find the equilibrium solutions by setting dy dt equal to 0 and then finding y's. I almost said just singular y, but really there might be multiple. So finding the y values where that happens. Now, the second thing you're going to do is draw a vertical line. I'll explain that in just a second of like why it's just a single vertical line. But you're going to draw a vertical line and you're going to mark the equilibrium points on it. Mark the equilibrium points. So I don't know, let's just a quick example here. Let's say that we get y equals 1 and y equals 2 from this. And we'll do some more examples. So you draw the line, you draw y equals 1, y equals 2. Then what you want to do is, so this is a third step, in between all of these equilibrium points, you want to mark which direction the derivative is going. So let's pick a point between the equilibrium points and plug it into dy dt and find if it's positive or negative. Now, this is going to require something else from Calc 1. Remember that if a derivative is positive, then the function is increasing. And if a derivative is negative, then a function is decreasing. And that's essentially what we're going to mark on this graph. So I don't know, let's just say that we get positive, negative, positive. So it goes increasing, mark that on the line, decreasing, and increasing. And so we're going to mark on those lines basically just if the derivative is increasing or decreasing. Now, what this does is we could extend this entire picture. So I could, after I get this phase line, I could say, all right, here is y equals 0. That's usually the t-axis. And then this we could say, let's make that the y-axis. And then in between here, all functions are going to increase up until 1. So I could draw that's an example of a solution where the initial condition is lower than 1. If y equals 1, it's a straight line because that is the solution right there. It's y equals 1. Y equals 2, that is the solution. Solutions decrease from 2 to 1, decrease from 2 to 1, and increase after 2. So now what I've really done is drawn almost a phase not a phase portrait, a slope field, but with some solutions in there. And really what this does is now we can say, all right, we have this initial condition. Let's say y of 0 equals 3. So if y of 0 equals 3 and I'm up here, well, then I know my solutions are going to go to infinity. It's a very fast way to figure that out. All right, so let's see. Do I need any more steps in here now that I just went off on a tangent talking about what the phase line does? So we draw the vertical line, we mark the equilibrium points, we pick a point, and we do that. Oh, and then the only other thing that we might want to do is classify. So a step 4 is to classify those equilibrium points if you're asked. And so here's some classifications. If all solutions go into an equilibrium point, kind of like we have at 1 over here on the left, then that would be classified as a stable equilibrium point. If all solutions go out of an equilibrium point, then that is called unstable. And do I have enough room to put one more in here? I hope so. If all solutions, or if some solutions go into and some solutions go out of, so that could look like either that or it could look like that, that is called semi-stable. All right, let's do an actual example. All right, so as an example, let's draw the phase line for, let's do dy dt equals k times 1 minus y over 1,000 times y for k greater than 0. Okay, so what we first need to do is find the equilibrium points. And to do that, what we want to do is take this dy dt and set it equal to 0. So we're going to take k times 1 minus y over 1,000 times y and set it equal to 0. And what we get out of this would be y equals 0. And I hope that's a little bit obvious. If we set y equal to 0, then this whole thing is 0. For this part in the parentheses, if we want that to equal 0 and give us 0, then y equals 1,000 would do that. 1,000 over 1,000 is 1, 1 minus 1 is 0. So y equals 0 or y equals 1,000, those are our equilibrium points. So we draw a vertical line, and we mark those on the vertical line. Now what we're going to do is pick points on each side of this vertical line. So up above 1,000, let's pick a nice number, like 2,000. You can pick any number above 1,000, but 2,000 is kind of nice. Now, if I take 2,000 and plug it into this differential equation, notice what I'm finding here is slope. Now, we don't need the number because all we care about is whether this function is increasing or decreasing, which means that all we care about is whether the derivative is positive or negative. So we don't need a number, we just need positive or negative. So what I would do is say, all right, well, k is positive. 1 minus 2,000 over 1,000. 2,000 over 1,000 is 2. 1 minus 2 is negative. And y is 2,000, so that's positive. And a positive times a negative is negative. And that would make the function decreasing there. Now let's do this again in between 1,000 and 0. Pick a nice number. How about 500? K is positive. Then 1 minus 500 over 1,000, so that's 1 minus a half. 1 minus 1/2 is positive. And then y is 500, and that's a positive number. And positive times positive times positive is positive, and that makes that function increasing in that segment. Below 0, pick a nice negative number. How about negative 1,000? So that means then what? K is positive. 1 minus negative 1,000 over 1,000. So that would be a positive quantity because we'd have minus a negative in there. We'd be adding something. It's positive. And then y itself is negative. Positive times negative is negative. And so that would make that function decreasing in there. Okay, so there's the phase line for that guy. Now, if we were to draw an entire, I could extend this and draw a really nice graph on this. So I could extend this 0 line, make that my t-axis. And actually, do you know what? Let me make this a different color just so that I can kind of state what I'm doing here. Let's go green. All right, so there's my t-axis. And really what I'm doing is I'm sketching some solutions. So sketch solutions to the differential equation. Now, I know one solution is 0. I know another solution is 1,000. And so if this, say, up here is my y-axis, then I've got when y is equal to 1,000, that's the solution no matter what. Now, up until 0, functions are decreasing. Now, these are always from left to right when we talk increasing and decreasing. So from left to right, this is decreasing. From 0 to 1,000, it's increasing. And from up above 1,000, it's decreasing. Now, these are approximate solutions. The concavity is approximate. And really what this does for us is it would be able to say, all right, what would happen if we had, say, changing color here, if we said y of 0 is equal to 250. And so what that means, if it's 250, is that it's right in here. Right? It's somewhere in there. And I know that solutions in that region increase. And so if I had that initial condition and I wanted to know what the long-term behavior is of this, what's going to happen as time goes to infinity, well, I could say that my solutions to that initial condition, y is going to approach 1,000. It's never going to cross it. It can't cross it because of existence and uniqueness. If you look back to that section, any equation that's like this is going to have unique solutions, and that means we'll never have a solution crossing on this. None of those green lines will cross. None of the orange lines, if I had other initial conditions, would cross. All right, now there's one other thing about this, and that's a kind of a specific verbiage on this. Let me find another color. This is going to look great when I'm done. All right, is that this initial, or this equilibrium solution 1,000, this is, can be called or referred to as an environmental carrying capacity. We're going to do an example that's actually really similar to this with these numbers, but with a real world scenario where, and the scenario is that you go to college and it's a college of 1,000 students and faculty and everything, and it's isolated. There's nobody else coming in and out except for those 1,000. And somebody comes back from Christmas break and they're sick. And so the question is, at what point or how long is it going to take for everybody to get sick? Or after 6 days, how many many people are sick. But what happens in this scenario is because the college only has 1,000 students, that's the carrying capacity. That's the maximum that could ever be sick. So if you look at this graph in terms of real world, we're not going to have zero anything. We're not going to have zero or below zero people sick. So that's not going to happen. You can almost ignore that part of the graph for this real world problem. Now above zero, if there's so many people sick, eventually there will be 1,000 people sick, but there can't be any more because there's no more people on campus. If there happened to be more than 1,000 people on campus in that scenario, then what would happen is that really more than 1,000 would be sick, but eventually would just level out and 1,000 people would be sick. So that's called the environmental carrying capacity. Okay, so now I have another example here. I'll make this one short. All I want to do is everything the same, except for that I want to change k to be negative. And what this is going to do is change all the arrows. I'm not going to go through that because now that you know how to do that, you can do this yourself. It just changes the direction of all the arrows when k is negative. Now, what this says is that everything from 1,000, this is an unstable equilibrium point, and we would call this a threshold level. And this, again, is kind of some verbiage that's used, especially when we talk about viruses and illnesses. And what this would say is that if you hit over 1,000 people with a certain virus, that virus is just going to explode. That virus is going to go crazy, and everybody's going to get it. If you can maintain that virus below 1,000 being sick, well, eventually you'll level off, and that virus will die out. So that's kind of an important word as far as studying viruses with these differential equations. All right, I think that's it for this video.